Unit 8, Part D, Network Services. The topics we're covering, a bunch of acronyms this time. ARP or ARP, DHCP, ICMP, SNMP, and our favorite, DNS. You'll learn what all these cryptic abbreviations mean soon. ARP, or Address Resolution Protocol. It translates network interface addresses layer 2 to IP address. Network interface addresses as a layer 2 address are only valid within your subnet, meaning your next door neighbor on the network connected to the same switch or hub you can talk to, provided that your service or application communicates via layer 2. Two problems with that. One is if you want to communicate to any device outside of the immediate subnet, you can't do it. You have to use a layer 3 address. The other being is that if the service you're talking to expects communication via layer 3 via IP, then you have to use the IP address. The layer 2 addresses are generally burned into the network interface card or the wireless card that you're using, whereas the IP address provides you with global communication. An IP address can get you anywhere in the world. A layer 2 address will get you to your next door neighbor. Network interface addresses are assigned layer 2 addresses by the manufacturer. The first few bytes, in fact, or octets of the MAC address, the layer 2 address, are assigned to manufacturers, so that's a good way to guess what sort of devices you have on your network is, look at the layer 2 addresses. They only work within the subnet. Getting outside the subnet, going anywhere else in the world, requires a layer 3 address. If the commuter wants to communicate by IP address, but doesn't know the IP address of the host that it's communicating, it sends a layer 2 broadcast asking who has this address. Excuse me, I got that backwards. If a computer wants to communicate by IP address anywhere, it sends a layer 2 broadcast asking who has the IP address and what is the MAC address I should send the frame to. So it's who has 10.1.1.1. I send that out as a broadcast. I get an answer. If 10.1.1.1 is on the subnet, it will respond with its own MAC address. I've got the MAC address. I requested the IP address. I'm happy. If the device is elsewhere, if it's not on your subnet, then the router, because it is the thing that is specifically designated to communicate with the outside world, will respond with its MAC address. So you'll say, give me address 192.168.1.8, which is outside of my subnet. The router will say, send it to me. Here's my MAC address. So you associate that outside address with the MAC address of the router. Either way, the communication goes to the right IP address. It's either in the network or not. Address Resolution Protocol threats. This is a security class, so I would be amiss if we didn't talk about security threats involving these protocols. A big one is cache poisoning. When a device asks what MAC address is associated with an IP address, once it gets a valid answer, it holds on to that answer a while. It reduces the amount of network traffic and the overhead involved in communicating if you don't constantly query for an IP address once you've got it. Problem is you store it in a cache. If the cache has incorrect information, you're using incorrect information for a while. For example, an attacker machine can deliberately respond with a wrong answer, and it can make you accept that answer as though it was legitimate by responding faster. That way, the attacker machine can intercept traffic. In this particular case, the evil or attacker machine on the local subnet may pretend to be the router. If it pretends to be the router, then any traffic going to the outside world, including internet sites, websites, your home banking site, ends up going through the attacker's machine on your subnet. It allows it to intercept all outbound traffic and can eavesdrop and modify the traffic before sending it to the real router. Other types of attack on ARP can overload a network with bad information, causing the denial of service, maybe causing routers and switches to behave in unusual ways. If you're interested, a tool called EtherCap is designed to facilitate the cache poisoning attack and to send bogus information that's kept in the cache. And that link, by the way, to YouTube is on the course website as well. Address Resolution Protocol. This is an example from my Windows machine of a dump of an ARP table. You see ARP-A. That's a command. It's actually the same command in Unix and in Mac, because Mac OS is actually a form of Unix. It's a common command to most platforms. It says ARP, dump the ARP table. And you see here we've got several different interfaces. This is my actual network interface. These interfaces belong to VMware. They are VMware client machines. If I were to spin up the machines, they would have one of these addresses. They still have ARP entries because they exist as machines inside of my physical machine. That address there, 192.168.1.2, is cache because it's the address of my local printer, and I print stuff quite a bit. So my machine has the mapping of the internet address to the physical or MAC address, so I can send print jobs to that MAC address via the physical. The 199 is my default gateway or my router. You know, if you look at the first few octets and look them up, you'll find out it belongs to Cisco. These other ones are various sorts of broadcast address. The 1.255 is the broadcast address for the entire subnet. The 224 and 239 are so-called multicast addresses that are broadcast addresses. And, you know, I'm not currently using multicast, but these broadcasts still exist. And then, of course, these other two are the VMware ARP tables. DHCP, Dynamic Host Configuration Protocol. You can set up your machine so that the IP address, the address of the gateway, the subnet mask, you know, how big is your subnet, what number ranges are considered part of your subnet, and you know, things like the DNS servers and so on are statically assigned. You can hard code that in your machine, which I've done on my desktop machine. Or more commonly, you can use DHCP, and this is particularly useful if you've got a portable machine like a laptop where you'll be plugging it into multiple networks and want to get it up and running very quickly. DHCP assigns network information at the device startup and can reassign it per request. It gives you the IP address, the gateway or router for outside traffic, and the subnet mask, which tells you what range of IP addresses constitutes the local network. It can also optionally give you additional information like a Windows Win server, DNS servers, and so on. How it works. The client requests network information via a broadcast. It says, you know, hey, is there a DHCP server out there? I need an IP address and all this other information assigned. The server on the subnet will respond to the broadcast with the available IP address as well as the other information. Now you can attack DHCP with fake clients or fake servers. A fake server will hand out IP addresses, default gateways, etc. to new machines that join the network. It may collide with a real DNS server, which is a problem, but as long as you can arrange to avoid that, you can configure machines with IP addresses and other network information of your choice, which can be useful to an attacker for traffic interception. Fake clients can request IP addresses and do other sorts of things. The other thing about DHCP is an unauthorized system can join your network as easily as a legitimate one unless you have controls against that. So it's kind of like anybody can plug into your network if they've got a live network jack. In general, they're on your network, whether they should be or not. Here's a little bit about how it works in Windows. You go to your network connections control panel. You know, I should note that this one here is the local area network connection, the actual hard-coded NIC, and these two, as mentioned previously in the ARP table, are the two virtual Ethernet adapters for my VMware instances. You go to your network connections, and in your local connection status, you can see that I've got IPv4 connectivity to the internet. You can see by the number of bytes in and out that, you know, there's quite a bit of traffic going on. And then you can look at the network connection details. And notice here, I have no DHCP enabled. I've got my address, my subnet mask, my gateway, my DNS servers, etc., but I've hard-coded them. The DHCP enabled would be set to yes for a portable machine or a laptop or a machine that wants to take advantage of DNS services. This may seem kind of a useless demonstration. I mean, I've walked you through this, and you see an example of my Windows 7 machine that doesn't use DHCP, but I'm showing you where to find this information on your machine. Oh, and by the way, this is the MAC address of my network interface. So somebody else asking for it via ARP will get that. Just as an aside, if that were yes, then all of these would be assigned automatically by a DHCP server on my network. Internet Control Message Protocol. It's a very old, very basic network management system designed to do things like let you know if a machine is up or not, let you know if there's a route available to a particular outside subnet, let you know if a router is up or down, etc. It supports a whole host of network management services. The ping utility, which you might be familiar with, usually uses ICMP, and it tests whether a remote host is actually up and responding to a request from your network. Traceroute, it's done by sending an ICMP echo request from the source. The target replies with the echo reply, and if I receive the echo reply, I know that the object of my ping is out there, and I can tell a few things, how many hops away it is in terms of number of routers between here and there, how long it takes the reply to get to me, what's the network latency, etc. Traceroute is another interesting tool. It's called TraceRT in Windows, and it tells you the total route taken to the target. You specify your target, and it will go hop by hop and tell you what all the intermediate routers are and how long it takes to get to each one. Sometimes this doesn't work because intermediate routers will not respond to ICMP and will not tell you where they are for security reasons and so forth. And ICMP also provides other messages that can tell you whether a network is reachable, is a router up or down, etc. ICMP attacks. Again, we have network attacks here. ICMP is so useful, it's often not blocked. It's generally allowed within networks and oftentimes allowed wide open to and from the internet because it's just very useful for determining if devices are up, where are they, how are they functioning, is there a router down, etc. It's kind of a protocol of last resort for network diagnostics, and for that reason is often allowed through routers, through firewalls, and across networks. It's not intended to do so, but it can hide hidden messages in the data portion of the packet and can be a devious way to communicate through firewalls and other blocks because it is open. You can actually use software called Loki to install a hacked version of the ping server and ping client and use ping as a way to transmit information between a secure internal corporate network and an arbitrary host outside. You know, the internal device just pings the outside and sends information from the inside out and vice versa. Attackers can also use ICMP to map your network and redirect traffic, find out what you've got, and do funny things with the direction of the traffic. Here's an example of how this all works. Ping command, pretty much the same in Linux and Mac OS. Here it is in Windows. The difference being is in Windows you only get a 4 ping requests before it times out. Most versions of Unix you have to tell it to time out after a certain number. It'll just keep running and running. It's pinging my default gateway with 32 bytes of data. It gets a reply, 32 bytes back, 1 millisecond time to live, which tells you something about how many routers are in between. Is 255 the max, so there's no routers between here and there. And then when it's done, it gives you statistics: how many packets were sent, how many received, how many lost, what's the round trip time minimum, maximum, and average. And this stuff is really useful for network diagnostics and knowing how well you can get to particular IP addresses. Simple Network Management Protocol, or SNMP. It's a UDP-based protocol, very early developed one for network management, still in very common use. If you've got a network management tool that goes out and gathers information about your devices, it probably uses this. It supports device management. It gathers information, stuff like how much traffic is going through an interface, how many packet errors, etc. What's the CPU usage on that device at this moment in time, how full is the disk, what's the memory utilization, etc. And it can also sometimes be configured to set parameters on devices. The device's SNMP agent responds to SNMP queries. You send the UDP packet to port 161, and if there's an agent there, it grabs it, interprets your request, and sends back the information you want. The agent gets information from something called the Devices Management Information Base, or MIB, which is a hierarchically organized directory of information about this current state of the device. The MIB is actually an abstract organization, a presentation of this information. Where it really comes from are hooks into the device's operating system that tell you things like CPU use and network traffic. MIBs may be generic. There are standard MIBs for things like network traffic through an interface, and there are vendor-specific MIBs. Cisco, for example, supports a good deal of vendor-specific MIBs that will give you information about Cisco-specific protocols and additional information beyond just the standard ones. You can't use those Cisco-specific MIBs, though, if you've got Juniper devices. They simply won't respond. SNMP is very useful to network managers, and it's also a great way for an attacker to figure out your network. Domain name service. The main purpose of domain name service is to map host names to IP address. The space of all names is split into zones. For each zone, there is a DNS server that is authoritative, that owns that zone and has primary responsibility for maintaining it and maintaining this mapping. The mapping is generally host names to IP addresses and standard DNS. You can also map things like mail servers and so forth. And you can do reverse mapping, which is given an IP address, what's the name of the server. There are also secondary DNS servers. They get information from the authoritative server, usually via a batch process called a zone transfer. If it's an internal secondary DNS server owned by the same organization responsible for that particular DNS zone, then you typically use a zone transfer. DNS handles both internal and external network names. Internal names are for servers that are accessed inside the organization only, like accountingsharepoint.company.com, which is only accessed by the accounting group inside company.com, for example, and shouldn't be presented or mapped for the outside world. Note that Microsoft Active Directory also advertises services, not just hosts, but actual services that Active Directory provides via SRV records. You want to know where a domain controller is, the SRV record will tell you. External DNS are for names and mappings that are required for public, outside customers and vendors to access. Your outside website, for example, an outside mail server as opposed to internal ones, will be mapped in an external DNS. Splitting your DNS namespace into internal and external names and having separate segregated servers handling one or the other is a very good practice. It's called split DNS, and what you're doing is ensuring that an outside party has restricted, almost minimal access to internal names that reveal things about the internal workings of your organization's network. Make sure that internal names and services are not advertised to the outside world as a matter of security. Here's an example of how DNS can work. The command here in Windows as well as Unix and Linux is NSLOOKUP, though Linux is deprecating NSLOOKUP in favor of something called DIG, which gives you a lot more detail but is not quite as user-friendly, I found. You actually have to really understand what DNS records, how they're stored, and what they look like internally. NSLOOKUP, I issue the command, it tells me, hey, here's the default DNS server I'm going to use. I'm going to use Google's that's at this easy-to-remember internet IP address out there. Then I get the little prompt here, and I say, okay, give me the IP address of IBM.com. Resolve that name to the address. Comes back with the server. Yep, here's who I am. I'm going to give you the non-authoritative answer because Google isn't authoritative for IBM's zone. IBM is authoritative for IBM's zone. But it gets it through secondary means, and it says, here's a non-authoritative answer. It's a hand-me-down answer. IBM.com is at this IP address, 129.42.38.1. Domain name service threats. Cache poisoning, as with ARP. You ask a DNS server, hey, what's the IP address associated with Bank of America? You get a response which is an IP address. You save it in your cache because you don't want to constantly have to look that address up for performance purposes and to reduce the network traffic on BFAs or your other domain name servers you're using. Cache poisoning is where this cached information is forced to be incorrect, where bad information is inserted into cache, and what that will do is direct a legitimate DNS name to a bogus IP address. You're no longer going to Bank of America, or you're going to an attacker in some foreign country with very lax law enforcement that's going to steal all your banking information. Say goodbye to what's in your Bank of America account because they now have it. You go to a clever replica of their site, you think it's Bank of America, you of course don't look at the IP address, and it's not BofA's IP address. Cyber squatting. This isn't really a threat against DNS as a technical service, but against DNS as a concept. It's, well, what's useful in the internet isn't IP addresses, it's names. The name is the brand, the name is where people actually will first try to go to. The IP address is just an arbitrary way of routing traffic. Well, what if I bought up a commercially valuable name and I refuse to relinquish it unless the rightful owner of that name forks over a whole lot of money? That's cyber squatting. A variant is typo squatting, where you look at, say, bankofamerica.com and you think, well, if somebody was going to make a typographical error, what type of an error would they make? And let me register that domain name, so if somebody makes a typo, I can do something with that. This is sometimes done legitimately. Bank of America may register the name, so you get sent to their site even if you put a typo in. Domain parking services may register it so they can serve up some advertising saying, and here's some Bank of America related stuff you're interested in, and by the way, here's a whole bunch of ads. Or an evil bad guy can register that typo, create their replica of the B of A site, and own you. Lastly, network mapping. If an attacker can use a zone transfer or other methods to get all the DNS records, they can find out a lot about your network configuration, what services are available, and just information that you don't want to be handing out to folks who don't need it, don't deserve it. And that's it.